All right, legends, this is Mr. Mays. We're coming through. We're going to look today at some pro tips for Unit 6. Now, keep in mind, I may throw in, I reserve the right to toss in a Unit 5 concept here and there, but let's remember that Unit 5 was all sampling distributions. Sampling distributions for means and sampling distributions for proportions. So with all of that in mind, that ties in beautifully with Unit 6, which of course we need all of those sampling proportion things in order to make estimations that we can then use to create a confidence interval. But Unit 6 is of course the confidence interval central, which of course, as you all know, is one of my favorite concepts of all time, if not my favorite concept of all time. So, some big concepts you should have in your back pocket, everything you should know for this. Now, first of all, you know this, go through your 6.1, 6.2, and 6.3 video notes. And be sure to look at the review guide. All of that is imperative. And if you haven't done that, you're probably missing some important information that you want to make sure you are salient on. And the key with this unit, as with every unit, is not just to know the ideas and be able to apply certain things, it's to truly be able to know them inside and out, okay? You've seen kind of the tricky type questions I like to throw in, and I want to make sure that you feel confident applying concepts in a variety of different ways, a plethora of different outcomes, right? So, things to be aware of. You should be able to interpret and construct a confidence interval, right? And you should be able, of course, to interpret or explain or clarify a confidence level. In other words, be able to say, what does it mean to be 99% confident? And I won't bother writing those out again. You should have them in your notes, and they're in the 6.1, 6.2, and 6.3 video notes a variety of times. But of course, when we interpret and construct a confidence interval, whether it's for proportions or for means, we're going to be doing the acronym PANIC, if you like to remember things via acronyms. And that will end with a conclusion where we say, I am blank % confident that my true population parameter is between blank and blank. And you should give context for that. Versus if you're interpreting a confidence level, this is where you say, if I had many samples or ran many samples, if I ran many samples, and they're all the same size, I'd expect blank % of the intervals that I collect from those samples, right? Because we would collect confidence intervals from each of them. And I would expect a certain percentage, depending on the confidence level. Again, 95% is the industry standard. So I would expect around 95% of those intervals to capture the true population proportion or population mean or population median, okay? Whatever the parameters that's being measured, that's what I'd expect it to capture. Beautiful, so that should all make sense. You should, of course, know margin of error, know how to solve for margin of error, right? Know that the margin of error is either, right, going to be a z-score, right, a critical value z times, for proportions, p hat times 1 minus p hat over n, the whole thing square rooted, right? Or, more often with means, it'll be a t critical value times the standard deviation of your sample over the square root of n, right? And on the rare occasion that it's a mean where we do a z-interval, again, that would be one where we do a z-critical value, but we are using the true population standard deviation over square root of n, and that will be made clear to you if the standard deviation is the population standard deviation. But most of the time, they give you the mean for that particular sample and the standard deviation for that sample, in which case you'll use a t critical value or a t interval, which you should know. All right, moving ever forward. Oh, and you should be able to calculate for n, right? This is what's called a power calculation, as you know. And in that power calculation, you should be able to go and solve for n, where you put your margin of error on the left and everything that margin of error represents on the right, okay? Be also available and aware of how to calculate your t critical value or your z critical value, right? That's area to the left. And then for z critical values, as you know, you're going to put in the data that's relevant there, versus for t critical values, you're going to be putting your degrees of freedom, which is your n sample size minus 1, right? So be able to run that kind of data work. For z critical values and t critical values, it's not a lot of effort that we have to go through, but it's of course in the norm if we're doing z critical values, right? Because we are working with the z-score, where we do area to the left, mean of equal to 0, and standard deviation equal to 1. And this, of course, is to get, and let me clarify that further, this, of course, all being to get the z critical values. But if I have to do a t distribution, right, and I need to find a t critical value, or if I set up an equation, and this is quite logical and quite likely, I might put a multiple choice question on there where I'm like, hey, which of these is the correct format? And I give you one that gives you the confidence interval, but it's written as your sample statistic, right, either your x bar or your sample proportion, plus or minus, and then a value, and then the square root of blah, 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 right? And whatever that situation is, something like this, right? Whatever it is. Oh, that would be the exact opposite, Mr. Mays. Hopefully you were looking and you were like, Mr. Mays, oh dear, this one up here is supposed to be the p-hat one, and this one down here would be the x-bar one. But either way, I might give you these and be like, well, which one's the right one? And you should be aware that that value here is either going to be a t critical value or a z critical value. And based on the problem and the information given, you should know which one it is and how to calculate it. Okay, so we've gone through all that. And we've said you need to know how to do power calculations. And you'll need to interpret the different formats. So the things I want you to be really aware of, you're going to have a formula sheet. But that said, it is no substitute for truly knowing what everything means and what it represents. So you should know the following two formulas, or actually the following three formulas, every which way, forward and backward, which shouldn't surprise you again. This, and then of course the third one being in the event that you have the true standard deviation, right, for the population. You should know these inside out and backwards, how to calculate them, how to run them in your calculator, right? Doing your different calculations under stats, tests, and whatnot, right? One prop z int, and then t interval. Similarly, though, you should be able to take this format and understand it and pull it apart, and there will definitely be multiple choice questions where you solve for particular parts. You should also be super salient on the fact that this is the margin of error, that everything after the plus or minus is the margin of error, and you should be able to do critical thinking and algebra skills there forward to be able to get calculations done for margin of error. Okay, let's do green. I'm feeling green now. So other things to be aware of, and this is mostly in the MCQ section, everything that I'm about to go through. No, and I tried to really push this home with you guys before we rolled in, but be sure you know the 10% rule. Be sure that you know that, first of all, that is the rule where 10 times your sample size must be less than the total population. And know 100% of the time that the reason we do that is to prove independence. And further, right, that's only to prove independence. That's the only thing it does, is prove independence. And know beyond that, that the reason that we need to prove independence is because otherwise we cannot trust values to actually have a standard deviation, right? So we can't have a standard deviation needed for standard deviation. 100% needed. Without this, we cannot have a standard deviation. For a sampling distribution, for any of these calculations, we need independence. Even our sample, to have a standard deviation, we need to have independence. So know that that is why that is the case. Okay, in terms of normal calculations, be aware, right, that the large counts condition, which is the whole n times p and n times 1 minus p, both must be greater than or equal to 10. And be aware that the reason why this is important, or I should say p hat, right? Because probably you're going to have p hat. The reason we have that, also the reason we have like the central limit theorem, right? And you should go through your notes and remember all this. But also the reason why we check, for example, with means, we check if the population is normal. Or, of course, with means, if we check to see if your sample distribution is normal. If any of these prove to be the case, of course, let's get that out of the way. If any of those prove to be the case, of course, what we've proven, please work with me, eraser. What we've proven effectively, it came back, is that we can treat the sampling distribution as normal. And what that allows us to do is to create normal calculations. And you should be aware that that's what those things do, and that's what causes them. This is also required for t-distributions, as you know from class. The rules are the same. Okay, and you should be aware of that. And then, of course, and I went over this in class as well, but be aware that the reason why we need randomness, it needs to say it's a random sample or a simple random sample or something. Randomness is important because that ensures that everything is representative. And if it's not representative, then we can't do anything with it. But that's super important. We need to be able to have a representative sample. Otherwise, the people that you've turned to create this sample and make these determinations, there's of no use to you, right? So it can't actually be proving any kind of point. Okay, so we know the reasons behind all of those things, and those should be very, very clear to us. Make sure to go through 6.1, 6.2, and 6.3 because they go into even more detail. Obviously know this, know when to do a t-test versus a z-test, right? Know when you're going in to go with a t-interval versus a z-interval. And of course, the determining factor is as follows. We do a z-interval for proportions, always. And for means, we do a z-interval if and only if we have the true population standard deviation. Then we do a z-interval. If not, right, we do a t-interval where we use the standard deviation of a single sample. But know that, live it, and love it. And remember our sort of distribution from class where we had one tall student stand up and a shorter student and myself on the tail ends to show what a t-distribution does, that it effectively changes to work with our sample's standard deviation. Remember, as always, let's go to a different color for this, that as n, your sample size, goes up, right? The larger the number of people that you've effectively worked with, your sampling distribution, the actual graph gets tighter, right? So like if this is a normal curve, right? And then I took this and I said, well, what if the sample size n of each one of the samples that make up this graph or these bars, however you want to create that distribution, what if it were to go up? Well, suddenly it would be a tighter and taller one. And effectively, at the end, if you had like sample size n equals like 50 million or whatever, we would eventually just have a single bar where everything averaged out to the exact standard deviation, or sorry, I should say to the exact mean, right? And that mean, or proportion, whatever it is, would effectively become the true population mean and the true population proportion, right? So just be aware that as n goes up, right, the further up n goes, the more we go from like this to like this to like this to like finally just like a singular peak, right? It just tightens up as your sample size go up. Now, mind you, not as the number of or samples that you put into your distribution goes up. That's not what matters. What matters is the sample size of each one of those samples. Beautiful, beautiful. Be aware that the central limit theorem, and I want to make sure that we're super clear on this. Be aware that the central limit theorem is saying that the distribution of sample means is approximately normal as long as n is greater than or equal to 30. And what I mean when I say that is, we are specifically with the central limit theorem, what it is focused on is whether or not the sampling distribution, right? So the sample means are normal. Those are the keywords there. So just be aware when we say central limit theorem, we're not saying that like your samples are approximately normal. We don't know that. We mean the sample means, the means of your samples. If we put those means onto a graph, those would be normally distributed. And you should know that because I'm definitely going to have some problem where I try and trick you. Excuse me, and I say it the right way, but I don't say sample means. or sample proportions. Either one will do. Or well, actually, it won't do. Actually, for central limit theorem, we don't really use sample proportions, right? We do large counts conditions. So just be aware that it's sample means that are normally distributed when we have the central limit theorem proven right. Okay. Guys, we're nearly there. This is actually not going to be too long of a pro tips video. Let's go perp. Mr. Maze loves purple. We know this about Mr. Maze. Every time I do the third person, I need to remember. Don't talk in third. All right. Know what a point estimate is. I mean, for crying out loud, I know it's so stupid. I think it's stupid. Frankly, we shouldn't have all these different words for the same thing. But welcome to every language on the planet, right? The point estimate, right, that is always p hat, or else it is x bar. Please don't come up to me and go, oh, what's point estimate again? You know what the point estimate is. It is the sample statistic, right? AKA the sample statistic. And be aware, right, that it is the center. It is found in the middle of your confidence interval, right? So if I have a confidence interval of like 0.5 to 0.85 or 86, let's say 0.86, and I said, let's say these were proportions, and I said, what's p hat? You should know what to do. You find the midpoint, right? You go 0.5 plus 0.86 and divide by 2. And that will find the midpoint between those two, and you will know that that's the center. Know that that will always be where the point estimate sits. If you are given a confidence interval, it is found in the very middle. And if you are given like a number plus or minus and a bunch of junk, you know that the point estimate is that number out front, right? It is the thing before the plus or minus, when the thing after the plus or minus is the margin of error. And this is just all being aware of like kind of the vernacular, the vocabulary, and where the data sits and everything, so that we know what we're dealing with and how we can use it to solve for what we're looking for. Remember that we normally put the lower value first, followed by the higher value, okay? And something I really want to hammer home that's really, really cool is if you think about it, and I will go into this in more detail in a second, but and you know this, as your confidence level goes up, right, your margin of error also goes up, right? It gets bigger, and therefore your confidence interval widens. So the surer that you are, right, let's say 99%, the bigger your margin of error will be, therefore the wider your possible values will be. Why? Because the possible plausible values, which as you know is what confidence intervals gives us, those possible plausible values, well, there are just more of them. That's why we're more confident. That or we went up on sample size. And similarly, the inverse would be true. If I had a lower confidence level, my margin of error goes down and my confidence interval is less wide. But be aware, if I were to take two confidence intervals from the same sample, they would have the same p hat. And that's important. So I will probably give you a question where I'm like, hey, if I change this from a 90% confidence sample to a 95% confidence sample or something like that, which one would be a likely candidate to be the confidence interval? And part of how you would suss that out, part of how you would determine it is make sure it has the same p hat. Because if we're pulling from the same sample it could be the same x bar as well. Actually, I don't remember which one I throw your way. It could be either. But you would know if you're pulling from the same sample, they would have the same sample statistic. Just some of those critical thinking skills I want to see, just zooming through your head. We know this. As sample size goes up, my confidence interval narrows. As sample size goes down, it widens, right? The same goes for margin of error, right? As n goes up, and I just said this over here, as sample size, and this is what I'm kind of adding to this, as sample size goes up, right, margin of error goes inverse to that. It goes down, right? We have a tighter margin of error, which is good. The more sample size, the tighter my margin of error will be, right? A thing that is kind of cool to think about is when you want to know, well, exactly how will that look? And this is a hint, hint, wink, wink, because I'm probably going to give something annoying like this. As my sample size n goes up by a certain factor, like let's say it's by a multiple, it actually, margin of error will go down by like a divisible of 1 over square root of n. And we know that because if you look at both margin of error calculations, it's either going to be, right, it's going to be a z critical value or more likely than not a t critical value with the standard deviation, p hat 1 minus p hat. But you'll notice they're both over square root of n. Over here, n is square root, and over here, n is square rooted, right? So if my sample size goes up by a multiple of a certain amount, oh, no, I don't want that. Ooh, and that's the crayon. We don't want that. Okay. So, but if it goes up by a certain multiple amount, right? Like, so if I'm like, I was sampling 5,000 people, but now I'm sampling 10,000 people. That's up by a multiple of 2, right? Or actually, this would be easier if I do times 4, right? So let's say I was sampling 5,000 people, and now I'm sampling 4 times that amount. I'm sampling 20,000 people, right? Was doing 5,000, but now I'm doing 20,000. Well, what I would say then is if I were jumping to 4 times as many people in my sample size, my margin of error is going to go down by about a half, right? Half of what it is, because it's 1 over square root of 4. And I know this because as sample size goes up, margin of error is going to go down. So I know it's going to be 1 over something by a divisible amount, right? And what it'll do is it's the square root of the sort of multiple that we find here. Now, you don't have to always do that, but you can do that if someone said, well, how would it change from one to the other? What would you expect to see the shift? So the secrets to be aware of here is that they change by factors of, so not something you add, but something you multiply by, factors of the square root of the change in n. But also just be aware, in the simple terms, that the margin of error will go up as sample size is lower, and as sample size goes up, margin of error goes down. All right. Remember, as always, when we say like I'm 95% confident, what I'm saying is 95% confidence intervals capture the true population parameter, right? 95% of the time. Remember that we are capturing the true population parameter. For the first time ever, right, we are talking about the population parameter. Confidence intervals are not talking about sample statistics. We use sample statistics, but we are looking to capture the true population parameter. And what we're saying is 95% of the time, right, we capture the true population parameter. But whatever that parameter is, we're almost always in this class doing proportions and means. But I want to sneak this in there. If the question says we did a sample of medians and we made a distribution of medians, what did we capture with a 95% confidence interval? Well, we would capture medians. So be aware, whatever the parameter is that I name in the question, and I say I do this interval, what would I expect to capture? Look closely. And that's the last thing I really want to leave you with, is look closely. My questions are tricky. Why? Because you're brilliant. You're ineffably brilliant. And I need to challenge you. As much as I want to prepare you by giving you as many pathways to success as possible, I want to drop you in front of my exam and see you show off, okay? Remember how capable you are. Remember how smart you are. And be aware that as you solve through these problems, you are going to be a mastermind. You know your stuff inside out and backwards. Now, again, just to clarify, we've gone through. I've given you every little pro tip I can. Watch them cleverly. Notice the things I have highlighted to you. Do not, though, feel like this is the sole thing you should do. In fact, above this gives you some tips, but above this, 6.1, 6.2, and 6.3 video notes and the review guide. Remember, I am here for you. Please come in early when I see you the day of your test. If you'd like to, I'll be there for advisory. I'm ready to roll with you, but just be aware, I adore being your teacher. Thank you so much for making my life as meaningful as it is. And I am 99% confident that you are going to do brilliantly on this exam, which means if I were to run samples, all of the same sample size, and take 99% confidence intervals for each of those samples, I would be confident that about 99% of those intervals captured the true proportion of students that nailed this exam. And the true proportion is, we hope, all. I believe in you. I'm thankful for you. This is Mr. Mays signing off.